Good morning, everyone, and thank you for being here. So, this talk is about our approach of developing a verified garbage collector from scratch through a proof-oriented programming approach where we co-develop programs and proofs together. Okay, so as the audience very well know, OCaml has powered several industries, starting from Jane Street's trading infrastructure to Hrefs search engine, Meta's Infer, and Flow. So all these companies depend on a crucial feature of OCaml, which is a rare combination, which is mathematical clarity of functional programming combined with runtime performance needed for real world. So in simple words, OCaml is equal to type safety, correctness, high performance, robustness, and reliability. Now, the big question is, all these guarantees depend on a crucial component of the runtime. It's the most fragile component of the runtime, which is called the garbage collector, which is written in C. Okay, so GC bugs are rare, but when they do occur, it's very hard to reproduce, subtle, and can crash everything. So we indeed need to verify the garbage collector formally. Okay, so let me introduce some of the features of the garbage collector that can attribute to its complexity. So a GC, in simple terms, its job is to free unreachable objects in the heap. For that, it has to handle different objects. It has to do internal pointer manipulations. It has to move objects from one heap to another. It has to do bit-level manipulations, deals with byte barriers, coalesces memory to avoid fragmentation, and sometimes, and from OCaml'25 onwards, it has to deal with concurrency and shared memory parallelism. So all these features have their own specifications and invariants, and the biggest challenge is all these invariants should work together to enable or preserve the reachability of live objects, and that's make GC hard to verify. Okay? So what's our correctness specification for verifying a GC? There are two specifications. One is safety requirement, which states that the GC should preserve live objects and should not corrupt it. Whereas the liveness requirement states that the GC should eventually free unreachable objects. But how do we verify the safety and liveness requirement? For that, we actually need to define what is reachability. And hold on, I will be reaching there soon. Okay? So if we start with verifying the GC from an existing code base, this looks like scaling the Mount Everest because there are a lot of intermingled specifications because of all those intricate features, and specification discovery is required for doing the verification, and it's become often unmanageable with an existing code base. So is there an alternate way is the next question we will ask. And yes, of course, there is an alternate way if we do a drop-in replacement of the OCaml GC with a verified one, of course. So for that, our choice is F* programming language, which helps us to develop a verified GC from scratch, and we can do drop-in replacement. And why we have chosen F*? Because F* has already proven its capability in doing drop-in replacement, most notably through Project Everest. Okay, and this is our approach in overall. So we model GC verification as an abstract graph reachability problem where the highest layer, that's the topmost layer, deals with a depth first search and graphs, as well as a verification of a depth first search traversal. It's just purely textbook-based algorithm implementation. And the second layer, we do a functional GC implementation where we implement enough features to do a drop-in replacement. Okay? And the third layer, and we implement a stop-the-world mark and sieve GC as of now. And the last layer, the concrete layer, implements the GC in a concrete memory model in low star. Low star is actually a subset of F*, which offers low-level features or like C memory model kind of thing. And finally, using the KaRaMel compiler, we extract the GC out, which is verified, and it is integrated with the OCaml 4.14.1 runtime, and we run benchmarks on top of that. It runs without crashes and gives reasonable performance as well. Okay, now we need to understand the layers one by one. So the first layer, the graph reachability and definition in F*. So how do we define the graph? So in F*, we define the graph as a record data type with vertices and edges. And reach is actually a predicate. Reachability is defined as an inductive predicate which takes us a graph as input and two vertices, and it has two constructors, which one is reach riffle and one is reach trans. Reach riffle simply states that a vertex is reachable from itself, whereas reach trans states that if there is an edge from z to y, and if z is reachable from x, then y is also reachable from x. And this is our specification for depth first search. Depth first search takes as input a graph, a stack, and a visited set, and it produces a visited set of visited elements. Okay, so what the post condition of our DFS traversal says that the DFS after the traversal is finished, that means when the stack is empty, the DFS traversal will stop, and when the traversal finishes, DFS produces all and only the reachable objects in the visited set. So it will add all and only the reachable objects. So this statement is not that easy to prove on F star because it runs on an SMT solver. So we need more preconditions to prove that. Why? Because mainly because DFS avoids certain paths which are part of the cycle. It avoids certain paths, so it's hard for the SMT to prove that it actually preserves reachability. Okay, so for that we need two conditions. One set for the forward direction and one set for the backward direction. The forward direction says that all the vertices in stack and the visited set are reachable from the root set, and the backward precondition states that all the vertices which are reachable from the stack or the visited set are either already in the visited set or there exists a vertex in the stack from which it is reachable. So note that this second precondition is exactly an intermediate invocation. It models the intermediate invocation of a DFS traversal. Using that, we are able to prove this property, and this is the most strong property which is required to preserve the reachability. Now, how do we construct a graph from a heap? So given a heap, we can construct the object graph as a pair of vertex and edges. V is a set of allocated object addresses in H, whereas E is set of pairs of the form XY, where XY is an element of vertex set and Y is a field pointer of X. Now, given a root set R, we can also construct the reachable subgraph such that it's a subgraph residing in G of H, which are reachable from R, where the vertices are reachable from R. Okay. Now, let us define the safety and liveness property in terms of our graph terminology. So, given an initial heap H1, the GC produces a final heap H2. We require that the initial heap should be well-formed. Well-formedness is essentially an invariant property which says that the heap should satisfy proper object layout, or it should obey object semantics, and there should not be any dangling pointers. So what our specification or the post condition of correctness says that in such circumstances, GC produces a well-formed heap where the graph is the reachable subgraph. The graph which is remaining after the GC is only reachable subgraph, and the non-pointer values of the reachable objects are all preserved. So if we are able to satisfy these three conditions, we can say that safety and liveness both are preserved. Now, I'm not going to introduce the OCaml object layout because the previous presenter already introduced about it. The important point to note here is that GC don't scan all objects. GC scan only objects whose tag is actually less than no scan tag. Okay, and we need to understand that if a field represents a pointer, then its last bit should be 0. The value of the last bit should be 0. I want to tell a little bit about mutually recursive closure object layout, because in our setting, in the OCaml setting, an object can point to the middle of an object. Okay, so that need to be understood. So if an object points to an object whose header is an infix tag, then that means it actually points to its parent closure. So every infix object is associated with a parent closure. Okay, and if the tag is not infix, then that means it normally points to that object itself. And one more thing we need to importantly note here is that for a closure object, the field start is different. For normal objects, the field start will be the first field. For a closure object, the field start will be the from the start of the environment. So these things are important to do a drop-in replacement. Now, let me introduce about mark and some part of our mark function. This is a piece of extracted code, C code, it's a piece of extracted verified C code. So mark takes as input a heap and a stack filled with roots, okay, and a stack pointer. And what it does is, it will pop out the top of the stack, colors it black, and it determines whether to scan the stack or not. When the stack is empty, it will stop its process, but how to decide whether to scan the stack is based on the tag. If it's no scan tag, if it's greater than no scan tag, it will not scan. So we need to do one more thing here. In order to prove the equivalence between mark and DFS, that means the first layer and the second layer, we need to say that mark is indeed a DFS. So we need to construct the object in such a way that the way mark traverses the heap, we need to reproduce the same thing for the graph construction. For example, if we are encountering an object with the tag no scan tag, it simply in graph it represents like a object without any outgoing edges. That means it's not no more need to traverse it. And field start, as I said already, field start is different for closure object and other objects. So in order to scan the fields of the object, we need to first determine its field start. So equivalently, for a closure object, when we encounter a closure object, the field start or the edges are constructed from the start of the environment, not from the first field. For all other objects, the edges are constructed from the first field onwards. And all the field pointers are part of the edge construction. Now, after constructing an object like that, we need to scan its fields. The mark has to scan its fields, right? So for scanning, while scanning, as I already said, if it encounters a field that points to an infix object, it has to make the pointee as the parent closure object instead of that infix object. And if it points to a non-infix object, the pointee is the object itself. So like that, we need to do the graph construction accordingly. So if we do this, we can indeed prove that mark indeed marks all reachable objects. So this is the way. So starting with an initial heap, we construct a graph G of H1 and we run DFS on top of that, taking a stack and visited set. And we run mark and we have two invariants in place. One says that all the gray objects in the heap is present in the stack and only in the stack, and all the black objects in the heap is present only in the visited set and only in the visited set. So these invariants are very important. Now, an important thing is that both DFS and mark should run the same stack, use the same stack, and each tail recursive call, so they are implemented as tail recursively. So each tail recursive call should ensure that both mark and DFS takes the same input stack in all the recursive invocations, and it terminates when the stack is empty. Now, DFS will produce a visited set, and we already proved that visited set will only contain all the reachable and only the reachable objects, and the mark, after the mark, we will prove that the graph remain unaltered because mark only does coloring operation, it's not changing any object pointers. And from these two condition, we know that we have an invariant which says that, which is maintained, all black objects are only found in the visited set. From these two condition, we can get that all the black objects after the mark is only presented in the visited set. And from these two conditions, we can actually prove that all black objects are present, all black objects are the only reachable objects in the heap after the mark, and rest are not reachable. So in this way, we can actually prove that mark indeed mark all reachable objects. Now let us see, this is not sufficient, mark marks and sweep has to preserve it, okay? So this is a snippet of sweep body, it's an extracted code. Sweep takes as input similarly a heap, a sweep head, and a free list pointer. Free list pointer actually points to the tail of the free list where we can add newly found freed objects, and sweep head is the position from where we start the sweep. Okay, now the thing is that what sweep does is it scans from the lower address of the heap to the higher address, and during its way, when it's encounter a white or blue object, it will convert it to a blue object. Similarly, when it encounters a black object, it will convert it to a white object. And we need to understand that those black objects are exactly the reachable objects, which are converted to white by sweep. Okay? And we need to understand one more thing. We are offering one more feature called sweep with coalescing, because if there is a coalescing operation, then two white objects can reside like this as two blue objects together this causes fragmentation. And with coalescing, we are actually ensuring that that doesn't happen. We merge the objects together, okay? So to extend or either to extend the free list or coalesce, this decision is depend upon whether the newly created blue object resides next to the free list pointer or not. If it resides next to the free list pointer, we will coalesce the adjacent blue objects together. Otherwise, we will just extend the free list. We just add the newly found free list blue object to the end of the free list. Now, mark and together preserves reachable subgraph, okay? So, like in order to see the when we preserve the reachable subgraph, it says it preserves the safety, and if it frees the unreachable object, it says it's liveness, but it's not that easy to prove in the presence of internal pointers. As I said, objects can point to the middle of the object in the presence of internal pointers as well as a coalescing operation. It's not that easy to prove. I will show an example. We have proved that all field pointers of black objects after mark are black already, and all black objects after mark are the only white objects after sweep. That also I have shown. Now, these conditions are not sufficient to prove that all field pointers of white objects after sweep are also white. And why do we need this proof? Because in order to say that the subgraph is preserved, we need to first construct the graph. So in order to construct the graph, the most important key condition, precondition is the graph is well formed after the sweep. So how to ensure that the graph is well formed? The allocated object should only point to allocated object. It should not point to a free object. Otherwise, it will cause a dangling pointer. So we need to first prove that the graph is well formed. So this is actually the well formedness property, okay? So in order to prove this property, these two conditions, we tend to believe that these two conditions are sufficient to prove, but it's not the case. We won't be able to prove this with these two conditions. That's why I already said the intermingled conditions are little bit hard to discover, and we are tempted to feel that these two conditions are essential, is the only condition, but that's not the case. We won't be able to prove. In order to prove that, we need two more extra conditions, which says that the field pointers of black objects should not be altered by sweep, as well as the tag and object size of infix and black objects should not be altered by sweep. So with that only, we will be able to prove the well-formedness condition. Okay, now it's easy, it's quite straightforward to prove that the reachable subgraph is preserved. Because suppose H2 is the heap after mark and suppose H3 is the heap after sweep, then we construct G of H3, the graph from that situation, and G of H3 is exactly the whites in H3, which is equal to the blacks in H2. And we also say that the field pointers are not manipulated, so that means it's not corrupted. And from this, we can say that G of H3 is indeed equal to Rg of H2R, which is equal to Rg of H1 of R. So that means the reachable subgraph residing in the initial heap, that is a heap before mark, is preserved in after sweep. And that offers safety. Now for liveness, we have to consider two things. There are two versions of sweep. One is sweep with coalescing and sweep without coalescing. So in sweep with coalescing, it's very straightforward, the liveness condition, because all whites are converted to blue, and that's actually the free object. So it's a one-to-one mapping. But in the case of sweep with coalescing, merging is happening with adjacent blue object. That means during the reasoning, we need to consider about the merging of objects, okay? So the sweep with coalescing's liveness condition says that either all white or blue objects are blue after the GC, or they are part of a blue object which is found earlier in the heap. So that's the precondition we needed. That's the postcondition we needed to prove that it preserves liveness. Now, and we also prove that no two adjacent blue objects exist after the GC. So there is no fragmentation. Now, this functional GC is over. Now we need to see what's the speciality of GC in low star. So one important thing to note here is that the GC in low star works on top of C memory model kind of thing. So it has fixed length buffers. So we encounter a problem called mark stack overflow. So in order to avoid that mark stack overflow, currently we have assumed that the stack is as large as the heap. And we prove a lemma which says that if the stack is as large as the heap, then mark stack overflow will not happen. Otherwise, we won't be able to type check the code in low star. Okay, so this is a caveat. So we will address it as a future work for more practical solution. And the other things we need to note that between the functional GC and the imperative GC, we need to maintain exact same order of operation to prove their equivalence. And we need to implement the GC in F star, which is a recursive GC. It should be a tail recursive one. And so that the iterative versions in the low star can be made equal because it corresponds to a tight wide loop kind of thing. And we need to devise suitable loop invariants to prove their equivalence. Okay, and we have done that, and this is we have extracted that and we have integrated with OCaml 4.14.1 runtime, and this is a verification effort. And you can see most of the lines of code are there in the layer 2, because layer 2 acts as the bridge between the abstract layer and the concrete layer. And this is our performance evaluation. So we can see that in almost all the benchmarks, so baseline is blue, verified GC is orange, and we include a Boehm GC also, which is yellow. So Boehm GC we have included, it's a conservative GC. We have included for the evaluation just because we want to show that our GC never underperforms a conservative GC. It's well below that, okay? So it performs more good. So, but in some cases we can notice that there is a less performance for our GC, especially for n-bodies benchmark, because we don't have a generational collection. And n-bodies benchmark actually does a lot of minor GC, so we don't have a generational GC, that's why. But as I said, we can't do everything at once. We have to incrementally add the features, and that's our next hope. And it is it's also integrated with the native compiler, and the benchmarking is work in progress. And how to apply the work directly to OCaml'5 as a question. So OCaml'5 is the latest one, right? We can still integrate, at least theoretically, but we won't be able to use the multi-core facility of OCaml'5. We can still run the programs in a parallel way, but we won't be able to use the multi-core facility. We need to stop all the domains. We need to allow only one domain to run, the stop the world GC, and there will be application posts we will experience. So that's it. And this is the overall summary. So we have implemented enough features to do the drop-in replacement, plus extra features like free list coalescing, free list maintenance, etc. And we have gained better insights through the process of specification discovery, so that we can make it for more sophisticated GCs. And this is an already published paper in Journal of Automated Reasoning, and I encourage all of the audience to read the paper. And there's a code repo also, which is publicly available, where our work is, we are adding our work in progress kind of thing. So please have a look at it. And that's it. Thank you.
Sure, that was amazing work, really well done. Do you think you can run the existing OCaml runtime alongside your garbage collector, so they can both run in parallel?
That is OCaml'5.
Yeah, so can you link them into the same process so that I could, for example, allocate some values into your stop the world
Yeah, we
collector?
need to do the integration. We haven't tried the integration, but theoretically it is possible.
Brilliant. This is very exciting. Well done.
Yeah.
Yeah, a very nice talk. You didn't mention anything about modeling compaction in this work.
Yes.
Have you handled compaction, or is that something to do in future?
This is not exactly the compaction. This is while doing the sweep, we discover we discover garbage objects. We turn it to blue, right? So that time we need to we are merging them for avoiding the fragmentation as much as possible.
Okay.
Yeah.
Okay. There's no other questions. I'll add another one. Could you say something about handling of like ephemerons or weak pointers or that sort of thing?
We haven't implemented those.
Okay.
Yeah.
No worries. Thank you.
Yeah.
That was the right choice.
Hey, very cool work. Congratulations. Is
Thank
there
you.
anything you would do differently in the design of the GC to make it easier to verify now that you've gone through that?
Okay. We need to follow the design of GC exactly like that, no? Like the specification says. Differently in the sense that, like for doing the formal verification, we need to exactly know how the implementation works. That only helps for specification discovery. And like honestly, in my experience, I just followed the specification as it is while designing the GC.
Cool. Sounds good. Thank you.
Yeah.
How far? Oh.
Yeah, so this is, I'll echo this is amazing work. So presumably the garbage collector will need to be improved and upgraded and so on and so on.
Yes.
How much effort will it be for you to update the specification and the proofs?
Yes, yes. So I want to mention that when I started this work, I have zero knowledge about garbage collectors, verification and F-star tool. So that's why it took so much time for me. But now with this experience, I don't think it will take too much of time. Because I already know how to tackle this verification. It's pretty easy.
So my question was almost the same. So how far are we from doing it for a full generation collector? Is it just we know how to do it, but it will take time, or there are limitations in the tools that we still don't know how to prove some certain things? Or
Okay. So in our extended paper, we have already given specification for a copying collector and an incremental garbage collector. I already given the specification, but we need to implement that, okay? But we have discovered the specification. Now, for OCaml 5, if we want to extend it to OCaml 5, it's a concurrent GC. It's a concurrent mark and seek GC. So we can't use low star. We have to use a concurrent, a language that supports concurrency. So we need to use pulse, like F-star pulse. We need to use, because our proofs, everything is on F-star. So F-star has another subset called pulse. So if we want to extend it to OCaml 5, we need to rewrite it in pulse. But that's also not a big deal. It's almost similar. Like if I know F-star, I can do that in pulse.
any other questions? All right. In this case, let's thank the speaker.